Okay, so like I mentioned in the last video, I'm going to go over the model specification of what constitutes a wrong regression model. So how do we know if the function we're regressing is actually the correct form? And so generally we can have two types of what a quote unquote wrong regression model is. So if it has bad functional form, so let's say we have like price and income, but we need to log our price because it's too high, or we need to square it, or to the power of 3 or whatnot. So either that's what makes it a wrong regression model, or we forget some of the important explanatory variables. So let's say for food expenditure, we had income and price as our determinants, but we also forgot about like what grocery we go to, and that might, if we forget that can potentially be a huge problem to our regression function. And so when we do that, we exclude when we do exclude important variables, the results are that our estimates are not only misleading but also biased. Um, so we've done residual plots and the Harku-Bera test um, to check for errors, which are kind of tools to how we can determine if we have the correct model specification. These are kind of more for like if our errors are normally distributed. So we haven't exactly learned our model specification methods. So in this video, we will use what we call the reset test and then the information criteria. So let's say theoretically our correct regression is given by here, and then this is our omitted regression. Excuse me. My cursor stopped working, but I guess that's fine. I could use my mouse. Okay, so we would say our unbiased. Okay, actually here the omitted regression is forgetting the beta 3 coefficient in our extra explanatory variable. So then we would say our unbiased estimator is the expectation of B2, which is beta 2. And then our biased estimator is saying that our omitted variable of beta 3 is included in the beta 2. And so this part of the beta 3 that's calculated inside of the beta 2 is what we call the omitted variable bias, because right here we kind of just assume that it takes in a part of beta 3 to determine our y output. On a side note, our bias, we have types of biases. So our bias in this case, not in this case, but our bias can be positive or negative if the determinants of the variable, so the covariance and then the beta 3 here, the variance will always be positive, so we don't have to worry about that. But if either of these are negative, then we will get a negative bias. If both of them are positive or negative, then we will get a positive bias. Something not too relevant, but just good to know down the road. So when we omit an important explanatory variable, that's again, that leads to a problem of bias. But another common error can occur where we add irrelevant variables. So what if our potential grocery variable is actually irrelevant, or our price of the products we're buying for our food expenditure is maybe irrelevant? And so we get problems of, so our problem is created of where our estimates are actually unbiased in this case compared to our omitted variable, which in this which in this example, it was biased. But for irrelevant variables, we get an unbiased estimator. However, we still get a problem of inflated errors. And that ultimately makes our estimates more imprecise. And a loss of precision is inflated when these not important variables we're adding are similar to our variables that we already have. So in our food expenditure, price, income, if we add like another wealth variable to our already next to our income variable, that would probably create the collinearity problem, as I will mention later. So how do we account for all these problems? We mentioned like the omitted variable problem, and then like bad functional form, additional irrelevant variables. And so what we will do is we will use these tools right here to determine our most efficient model. One common way of doing that is what we call the adjusted R squared. So we went over the R squared and how that's called the goodness of fit, how that measures our correlation of our explanatory variables in our output. The problem about the R squared is that it doesn't account for the number of coefficients in our regression function. So if we have like beta 2, beta 3, beta 4, beta 5, whatnot, then our regular R squared will become inflated or increase because it doesn't account for, if some of the explanatory variables we added are irrelevant. However, the adjusted R squared actually does. So the adjusted R squared can be given by the formula here. So similar to a regular R squared, except here we're also accounting for the number of coefficients, so n minus k. And so mathematically, we can see the trends of, let's say we add more variables in order to decrease the sum of squared errors. If we do that, the regular R squared would just naturally decrease or increase because we have a better goodness of fit based on our addition of explanatory variables. But in our adjusted R squared, if we increase our coefficients, then although this part is getting smaller, we increase our coefficients, so k increases, and so n minus k becomes smaller. And then so this whole part of the data right here, or the function right here, that becomes bigger as SSE becomes smaller. So it's kind of hard to see, but if you kind of just went over what I said, then you'll realize that the adjusted R squared kind of compensates for our addition of explanatory variables, and it kind of punishes us for saying, hey, some of our variables might be irrelevant. More isn't necessarily more, sometimes less is more, whatnot. But I think in general, adjusted R squared will increase just gradually as we increase our coefficients, just not as much as the regular R squared. Two other parts of the information criteria mathematically can be seen here is called the AIC and the BIC. I forgot what they're short for, or what they stand for, but generally this whole function formula here, we don't usually compute it by hand. Usually we kind of ask the software to do this. Same with the R squared and all of this, but intuitively we can kind of see the trends. So as our SSE decreases, then our AIC will also decrease. As our coefficient increase, then our AIC will also increase. As our sample size increases, AIC decreases and BIC decreases. And so generally, in contrast to the adjusted R squared, we want our AIC and BIC to be lowered. And so the lower our AIC or BIC is, the better it means that our functional form is better. So usually we would have, like, if we're testing for many different functional forms, we would just choose the one with the lowest AIC, BIC, or the highest adjusted R squared. And so kind of in summary, if we have the wrong functional form, so x or x squared or log x, then we violate the multiple regression assumption because then it has no linearity aspect, and we get biased estimates. In the omitted variable problem, we also get a biased estimate because this is not necessarily an MR assumption, but it's a result of it. In the case where our x variables and our errors have a noticeable relationship. And then our irrelevant variables, this doesn't create a bias. It's not a violation of the multiple regression assumption. However, there is a loss in precision as we get inflated errors. And so, okay, I think I'll go over what like this exactly means in the next video. I don't have it written down, but I will go over what like the distinguish how these are actually different later. Okay, so I mentioned, besides the information criteria, I mentioned the reset test, also called the reset test is a part of the post-evaluation analysis. And that what it does is it tests if the model has a correct functional form. So over here. All right. So usually done by software, and so it will kind of go over like many possibilities of the correct model, usually like squared or interaction variables, I guess, would also account for, but mostly versions of like squared or log or cubed, or like E, I guess, probably not E, but so on a software, how it would use the F statistic of a joint hypothesis, what we went over in the last video, and that's how it will get its results. All right. So like I mentioned earlier, the problem with collinearity, if we have similar explanatory variables of like income and wealth to food expenditure, these beta 2 and beta 3 are less likely significant because they are so similar to each other. So when we're testing if either of them are significant, then this collinearity aspect onto our regression function becomes a big problem. All right, so how do we correct for this? We'll use what we call the auxiliary model. And so it will regress an explanatory variable on the rest of the explanatory variables. So that's kind of confusing because normally we regress on just the y variable. But intuitively, we can just kind of say that we're finding the relationship between the variable we're testing for collinearity and then the other ones that potentially might have collinearity. And so we regress, and then we'll find the goodness of fit based on this regression function. And so if that R squared of the auxiliary model is high, usually an 0.8 threshold, then we conclude that there is collinearity, and thus we drop this coefficient right here. If the R squared is high and then the X squared is collinear to like X3, then we could, we might want to drop out X3, but we still want to, if we want to drop out X3 over X2, we would still have to regress X3 onto the other explanatory variables if we want to do that. But yeah. All right, so that's a brief overview of how the model specification works in a regression function. This is very applicable to any projects or experiments that we want to do, even outside of just data science. So very important. All right. In the next video, I'm going to go over indicator/binary variables. So variables I can take on that only take on a value of 0 to 1.